I'm muted. John muted me.
You are actually off screen right now, but I can make you on screen. Do you want us to talk?
I can just move this over if you want.
I'll do this.
You still see the...
All right.
Okay.
All right. Good evening, everybody. Welcome to our second to the last Twed of the spring 2018 term. Next week is what?
Lightning Talks.
What?
Lightning Talks.
All right. Next week is Lightning Talks. And has everybody signed up for Lightning Talks?
Yes, John.
Okay. Well, I'll send out 5 more emails anyway, just to make sure. So just a couple logistical things on my current behavior to the contrary. We are actually streaming live. We record these for posterity. We promise that we've got the audio working properly this time. So any of our distinguished Constellation professors who might be monitoring this won't get a crappy feed. For his nth Twed, we welcome Matt to talk through his latest incarnation of his deep learning and CNN stuff.
Yeah.
And pasta classification.
Yes, there's pasta in here.
There's pasta. There'll be pasta. Katie was saying, so are we having extra pasta for?
Oh,
that's right.
That would have been.
So, feel free to ask questions as
Please.
Matt goes along. I know that this is attendance shows that there's acute interest in this. So, take it away, Matt.
Thank you. Yeah. So I'm Matt. This is going to be a little bit more of an open-ended talk. So it's an idea that I've come up with fairly recently, and I'm actually looking for feedback, and hopefully people have some good suggestions that help me graduate. So that would be awesome. If you have ideas on extensions or future directions of this work, or see something wrong with it, please let me know as we go along. So the title is Improving Classifiers with Knowledge Graphs, and we're just going to recap some basic terminology before we kind of dive into it. So just starting off with a why you should care kind of slide. There are a number of applications for training classifiers. So spam filtering has been around for a long time. The task being to, if you're receiving an incoming email based on some keywords that it has in it, decide whether it's spam or whether it's not spam. So it's a binary classification problem in which you're trying to assign one of two classes to an input. You can try to guess what language something is based off of its classifiers. I think we lost the color again a little bit. We'll come back. There we go. Sentiment analysis, you trying to classify whether something that somebody said is positive or negative, and on and on. Maybe one of the more important classification applications is in self-driving cars. You're trying to decide whether or not there is a person in front of you or not. And recently, there's been some high-profile instances in which that sort of thing has failed. So it's an important problem to look at. And just to put it a little bit more formally, or describe how you might go about training a classifier traditionally, you gather some input data. So we're going to be dealing with supervised classification, which means that our input data has associated classes given to us at training time so that we can learn a model that will predict a class given some input. And then we actually train the model to map from our input data to labels, and then you deploy it in the application that you're interested in. So in this case, we have an example of a classifier that receives some images of cartoons and has to decide whether or not they're a duck or not a duck. And supervised learning receives those labels and those inputs together and learns a function to map from the inputs to the labels. So one potential problem with the setup as I've described it is that these labels are essentially just numbers. So you can replace duck with 0 and not duck with 1, and the problem formulation doesn't change at all, right? There's no meaningful information necessarily that's surrounding those labels that could give you any aid in tackling your classification problem. So, as we've described it, any extra information that you might include about these labels, aside from the inputs, is not there. So to kind of get a handle on what that looks like in terms of various machine learning methods that are used today, I'm going to talk about machine learning in a traditional sense, where you have some human extracted features that are serving as your input to your classifier that you're trying to train, and also deep learning, which essentially takes care of that feature extraction portion of things first. And we'll look at some examples. So in traditional classification, you might have some information about the classes built into the features. So for example, this is a famous iris classification data set where you're trying to determine, what species of iris a particular flower is, and you're given features like the petal length, the petal width, a bunch of other things. I'm not a botanist, I don't remember all of them. But in this scenario, these features are sort of hand selected, right? Some human has entered the petal length and petal width of all of these different flowers, and that gives you some information about the classes, right? You can say that these these different kinds of flower all have petals, they all have whatever else, but the human annotation part of that is expensive, right? It takes somebody that's experienced to determine what the important features are here and try to feed it into a classifier. In contrast, deep learning type approaches don't require on that kind of feature selection. So you could just feed an image of these different kinds of irises, and it would hopefully learn some features that were important for recognizing what kind of species they were. However, the features that it learns are not necessarily don't necessarily utilize any known information about a class. So the features that it's gathering might not correspond to the petal width or the petal length. They might be something totally different. And that can be a good thing, but it can also be a bad thing, because that means that deep models have the potential to fail in unexpected ways. So sort of just to help you visualize what that looks like, if we have a deep architecture out here on the right that's been trained to classify faces, map a particular an image of somebody's face to a label that describes who that person is. Typically what happens in these deep architectures is that a hierarchy of features is learned. So at the bottom level, you have very simple features like edges or different color filters that feed into higher and higher layers that start to maybe recognize things that look more like something a human would use to recognize somebody's face, detecting whether or not there's a nose in the picture or something like that. But again, those features are not necessarily the symbolic features that we would hope to use as a human in identifying somebody. So, is this a problem? Is it a problem that we're not necessarily including information about these classes that we're predicting in the classification training phase? In the first case, we were including some information. These features that we're feeding into the model have some, if you want to call it semantic information about what the classes are that it's predicting. But there's a reason that deep models are more popular when you are trying to train a classifier, and that's because coming up with the perfect feature for predicting some class is difficult. And deep models often come up with better features for classification than do these traditional models. So the question that I've kind of been wrestling with is, can you have the best of both worlds? Can you have something that doesn't require a hand-created feature as input that still incorporates some information about the classes that it's predicting to help with its prediction, right? So that's where I think knowledge graphs may be able to come in. So a knowledge graph is just a graph of concepts in which concepts relate to one another via these edges, and they can describe what information about classes, such as how they relate to other classes, what attributes they might have, etc. And when I say knowledge graph, there's been a debate within Tetherless World, right as Jim walks in, about what actually a knowledge graph is. In this case, I'm just considering a label directed graph, meaning that each of these nodes and edges has some label associated with them, and Jim gave me the shrug, and there's a direction on the edges. So a knowledge graph could potentially help inform a classifier about the objects that it's actually trying to classify. That's sort of my hypothesis. There's a lot of information contained within these, and I think that we may be able to make use of it during a training process without having to resort to some like handcrafted features or something along those lines, like we saw in the Iris dataset. So yeah, I ask all these questions. Can we use it to a knowledge graph to give hints to a deep classifier about what features it might want to learn? Can it serve as input to a classifier to give more information than a label alone, or maybe it can improve a classifier's utility, not just for classification, but if it has an understanding of, if a classifier has within its vocabulary the concepts that surround the classes versus just the classes themselves, then maybe the classifier suddenly becomes useful for a task beyond that which it was originally intended. So then the big question is, maybe all of these things are true, but obviously the burden is on me to show that some of them are possible. So in this talk, I'm going to describe how I think rephrasing these original classes might be able to help inform a classifier during training and produce a better, by some metric, classifier in the end. And I'll discuss techniques for learning from these sort of reformulations or rephrasals or whatever you want to call them. I'll show some really early results on some experiments that I've been running on some deep models trained on birds dataset. I'll get to that in a second. And also discuss how, based on the way that I'm training this classifier, how can the classifier be repurposed with this extra information that it's got now about these classes that it's actually classifying in order to do something cool, do something that's potentially more interesting than just a single classification by itself. And then the future directions is where I hope that I'll get some input and we can have a discussion. So I've explained the benefits of a deep model versus a traditional machine learning model in that you don't have to specify features ahead of time. That also, based on the way that these deep models train, they learn their own features that are statistically correlated to getting good results on some target loss that you're training it on, right? For trying to force a deep model to learn features that you kind of think it should be learning by, playing with the weights within the network or, trying to directly affect the training process is difficult. So people have tried and largely failed to develop regularizers that make deep models learn things that are similar to what a human would learn, right? They're black box architectures. It's really hard to manipulate the training process in any kind of way that's accomplishing that goal. So rather than trying to influence it directly, maybe it's possible to influence it indirectly. And what I mean by that is, rather than trying to force it to learn specific features by altering the weights that go on within a deep model, maybe it's possible just by showing it examples that fall outside of the original classification task that we can indirectly influence it to learn some things that are important. So for example, rather than predicting, whether something is a duck or not a duck, and have that be it and learn its own features for doing that, maybe we can also show it examples of things that have wings, things that have bills, because we believe that these are features that might help it learn later on to classify a duck correctly. So that's kind of the idea that I have. So as an example of that, if we have some information about, a duck that or some bird that we're trying to predict, like what sound it makes or what kind of feet it has, maybe rather than training only on the label of a duck, we can also train it that, hey, this image that I'm giving you is a bird that makes a quack sound or a bird that has webbed feet. And the idea there is that if you vary this if you can come up with enough examples outside of your original training data set, you would think that your model might be kind of forced to pick up on some of these features that exist within the knowledge graph surrounding these classes. So, if it can correctly identify that something has webbed feet, later on, in theory, that ought to help it in differentiating between a duck and an owl. Yeah?
So why would this guarantee that the internal structure would necessarily have more information in it than just the product of those three, in this case, separate classification tasks or prediction tasks?
More information in it than...
So that it would separately... So one possible outcome from this is that it could... you could have three different models. One that predicts from the image duck or owl, one that predicts from the image quack or food, and one that predicts from the image webbed or talons.
So you're using
you wouldn't necessarily have all of that integrated.
You'd be using the same architecture for the three problems, right?
Mm-hmm.
So in the architecture that I'll discuss later on, it's based off of an image captioning architecture, right? If we take as input an image, we're trying to produce essentially a series of tokens that correspond to what it thinks is going on in the image. If we train that on multiple targets for a single image, then necessarily the updates within the weights are going to have to reflect some back propagation that's been trained on these three tasks together, right? So you would imagine that if it's going to achieve if it generalizes well and can predict and get decently low error after training on all of these tasks, then in some sense it must have integrated information that's useful for predicting these tasks. Now, whether or not that corresponds exactly to, I can definitely tell that this thing has webbed feet and that makes it a duck, I don't think that you're going to achieve that level of clarity in terms of the features. But the hope is that you're at least giving it some information about what's going on in these images.
Okay.
So the big question then is, if we have a knowledge graph, how do we create that sort of, how do we generate that extra training data so that we can help our model learn these things that we think might be important, right? So in this scenario, what I'm considering is concepts that appear in the direct vicinity of a class in a graph. So if we have duck, the class duck that appears in a graph, and we know these various things about it, all I'm considering is information that can be had from the nodes and edges that appear that are incident to this particular duck class node. So I'm not doing anything more sophisticated like inferring anything about a duck that might be that you might be able to infer based off of like some chain of nodes and edges that you have in the graph. I'm only looking in the immediate vicinity. So this is a big area of improvement that I am considering for future work, and we can talk about that at the end. But just for now, when I'm saying that I'm going to generate these extra training labels, if you will, for these input images, what I mean is that I'm only going to look at the edge types that are coming out of this duck and use those as the extra tasks.
So you're not, so it's these and only these. You're not sort of having optional things. Oh, by the way, I also see this. Oh, by the way, it's also colored this. You're not so you're not kind of arbitrarily decorating this node based on, or this class based on things that you're finding. You're saying you're looking for these.
Oh no, sorry, no, it is arbitrary.
Oh, okay.
Yeah. So if those nodes appear, only one edge away from this class that we're interested in, then it's going to be included. And there's a potential problem with that I'll get to in a second. So the idea that I had was, I want to assume as few things as possible about the knowledge graph. I don't want to do anything like, if I have an is-a relationship here, like a duck is a waterfowl, then I could, in theory, if I know that is-a is a transitive relationship, I could go all the way back up the chain and say this duck is actually, a bird. But in this case, I'm not doing that. I'm only looking at the nodes that are within the vicinity, but I'm not being particular about which of the nodes I was looking for in the first place. It just has to be within that immediate neighborhood. Make sense?
Also,
Yeah.
does that mean you're doing multi-label classification tasks?
Sort of. So I'm not necessarily trying to predict all of these at once. I might show as an example to my classifier that this is a thing that is a waterfowl in one training example, and then later on I might show it that this is a thing that is a waterfowl that also has webbed feet or something like that, right? So it's not. I'm not necessarily predicting that this is a waterfowl and this thing has webbed feet all at the same time, although that is something that I do. Eventually, I break it down into its subtasks in a way that I'll describe.
Okay, and by the way, so how do you make sure that? So what if your original image actually does not have enough information to classify all those like sublabels?
Yeah. So that's one of the challenges that I'll get to in just a second. Yeah.
So that encoding, or that sort of sounds like you're implying an encoding where like the output can have a bunch of different types rather than the output being like a list of RDF triples. Is that the case, or like what are the trade-offs of those different output encodings?
So there are a number of outputs for a single input in this case. So what I'm training on is the subsets of the edges and nodes that appear within just one within the neighborhood of this class that I'm originally interested in. So
is that like a fixed size?
No. So
or a variable length.
So that's what I was just saying is there's one training example might be this is an image of a duck. The next training example might be this is the image of something that has webbed feet. The next training example might be this is the image of a duck that has webbed feet. So it's got these combinations of these different things that are, and the idea being, to learn to learn more interesting things about this class. If I show it a bunch of these labels, it will hopefully pick up on at least some of these characteristics and integrate that into its weights.
Okay.
Say that the number of outputs are like 3 outputs, right? So basically, one of it is a class, one of it is a caption, and one of it is the knowledge graph and any of them. So it's like how many networks?
No. So
network,
I'll get to the architecture in a little bit, but we use the same architecture for all of those cases. So it's essentially just a variable length sequence that's the target that you're trying to learn, and that for the same image you can have multiple sequences.
How do you set the length that something long caption? You basically restrict the length.
So that's more of a question for a deep learning. So one way to do it is just to have it, a maximum length that you set ahead of time, and then add it with zeros when you don't have anything beyond like 3 things to say or something like that. So yeah, there are a lot of deep learning techniques. The image captioners that are deep learning based are pretty sophisticated in terms of dealing with variable output sizes.
Yeah, if there's an edge says that is something, will you include that something into your label set?
Yeah, so these nodes that are on the receiving end of these edges also must be included into the vocabulary, but it doesn't mean that I'm going to. So if it's like duck eats fish or something like that, then yes, fish is something that I'm also including in my output vocabulary and therefore sort of classifying. So there are a few potential problems that were very briefly touched upon. One of which is that if I have all of this extra information that surrounds a class, such as a duck makes a sound, makes a quacking sound or something like that, that might not be helpful to my classifier in terms of actually learning anything. So you can imagine, based off of an image, it might be kind of difficult to tell what sound an animal in an image makes, right? So it's possible that you're coming up with extra information that will only confuse your classifier instead of actually helping it learn something that's progressing it towards its original goal. And further, we talked a little bit about these variable length sequences. If I have a lot of information that's around that central class node that I'm interested in, it's going to be very difficult to do a multi-label classification and predict it all at the same time, right? In some of the bigger databases, or if you were to look at entities in DBpedia, for example, they might have hundreds of facts about the entities that appear. And obviously, predicting all of those at once is a very challenging problem. My idea is that it would be good to allow your classifier to let you know as you're training what kind of site information is helpful toward what kind of things it can pick up on, and what things are just very impossible. So if we were training on people instead of ducks, and this is maybe a better example. If I have in DBpedia, the information about where somebody was born, it's nearly impossible to classify where somebody was born just based on looking at a picture of them, right? So that's something that my classifier, I wouldn't expect it to do well on, and something that I probably shouldn't be using to help train. So the question is, how do you guide your classifier to use the information that is helpful and sort of ignore the stuff that is not helpful? So what we really need is a meta algorithm that's supervising what the classifier is learning and adjusts the kinds of examples that it gives based off of how well the classifier seems to be doing in terms of picking those things up. So not wasting times on an impossible task like trying to determine where somebody's from. So there are a few criteria for this kind of algorithm. We'd want it to be able to learn in an online fashion. These training batches during the supervised training of something like a deep neural network come in one at a time. And it's helpful to be able to, if we want to be able to not waste a bunch of time, what we'd want is something that can monitor example by example and see, oh, this is something that seems to be working. This is something that doesn't seem to be working. Obviously, it needs to work with some kind of feedback from the classifier, because after all, we are trying to determine what the classifier is doing well at and what it's not doing well at. And mathematical guarantees are always a nice thing. So if we can sort of minimize how bad our classifier does, or how bad the training examples to our classifier are, that would be great. So this is where a technique from reinforcement learning comes in. It's called multi-armed bandits. And the task of multi-armed bandits is given some arms, some actions that have an associated reward. The task is to play the arms one at a time. You observe the loss or the reward of a particular arm at one given time, and then you have to adjust your strategy as time goes on. So it gets its name from a colloquial term for a slot machine, which is they call it the one-arm bandit, because you pull the one arm and then you lose all your money. So in the multi-arm bandit scenario, we pretend you have access to an entire casino's full of arms, and the goal is to figure out which arm, just by playing them one at a time, is going to give you the best payoff in the long run, right? So how much you're trying to, in the multi-arm bandit parlance, minimize your regret. They define regret as how much your actions differed from the best overall strategy over time. So if there's one slot machine in the corner that always pays off, you want to, based on exploring all of them and actually figuring that out, during that time period, you want to minimize how much money you're losing compared to how much money you could have been making by pulling the best arm all the time. So in our case, if you haven't gotten the analogy quite yet, the arms are going to correspond to these different collections of information that we have in the knowledge graph, right? So one arm might be predicting something that has webbed feet. Another arm might be predicting something that has webbed feet and also has oily feathers. And the goal is to get our, using this algorithm, or using an algorithm suited for the multi-armed bandit task, the goal is to feed the best information that we can to our classifier. So these payoffs that an arm gives you, how much money you win if you pull a slot machine, there are two main ones in the multi-armed bandit literature that people consider. The first is stochastic payoffs, where the payoff rewards are independent and identically distributed. And in the adversarial assumption, they are not. So as it turns out, you can expect to do better if the rewards are stochastic versus adversarial, because that means somebody could be looking at your strategy and saying, I'm going to change the, I see that you've been playing this arm a lot because it was paying out. I'm going to change that, and now this arm isn't going to pay out. So obviously you're going to do worse if somebody's actively going against you. Usually you can assume to do better than in the full adversarial assumption, because typically there's not actually somebody behind the scenes that's looking at what you're doing and trying to go against you. But in our scenario, we do have to consider the adversarial scenario, because these arms that we're pulling, they're actually resulting in a change in our network, right? If I'm training on something that has webbed feet, that means that my classifier has learned from that now, and the next time I pull that arm, because my network has changed, I might get a different reward than what I could have expected before. And that's those two rewards have a dependence there, so it's clear that they're not IID. So there's actually a technique that's almost perfect for the task as I've described it. So this was a paper that came out last year called Automated Curriculum Learning for Deep Neural Networks, or something along those lines. Oh, it's right there. I wrote it on the slide. Automated Curriculum Learning for Neural Networks. So we've seen this multi-armed bandit problem be applied to training neural networks by selecting a curriculum for the networks, and that's essentially what we're doing. So real quick, curriculum learning refers to the process of training something on easy examples first and hard examples later. Traditionally, this has been big in things like translation. So if you're trying to train a model to translate from English to French or something like that, you started off with nice, easy, simple, short sentences, and then progress as things get harder. Or progress to longer and longer sentences, because it's assumed that the longer sentences are harder. So one problem with going with a straightforward curriculum setting is that if I'm in our setting, is that if I'm gathering information from a knowledge base, I don't necessarily have any intuition about what things are going to be easy or hard for this to learn. So I need to use this bandit scenario in order to help supervise that and learn as I go what things the network is finding easy or hard to do. And it satisfies those criteria that we were looking at before. So it works in an online setting. We are allowing the network to indicate what is easy via these bandit payoffs, and these algorithms for solving these bandit problems have mathematical guarantees about you're limiting your regret in terms of how many examples you feed your network. So you're limiting your regret in terms of if I showed the network the optimal example every time versus what I actually did, how much can I expect those two things to differ? So that's always nice. We know that we're not doing arbitrarily bad on the problem. So one thing that I've kind of glossed over to this point is what kind of payoff you're actually going to use for this scenario. So I say we want to see what the network thinks is easy and what it thinks is hard. Well, how do you actually quantify what's easy and what's hard? This paper explored a total of 8 different metrics for measuring these payoffs. For our discussion, we're going to examine the difference in the loss before you train on an example and the difference after. So recalling how a supervised deep learning algorithm works, you feed it some input example. So for example, I have a picture of a duck and I'm trying to predict that it's a duck. And I see that I did poorly on this and that's quantified by some loss function that you have that you're trying to train on. That information then gets propagated back through the network so that it does better next time. And what you can do is you can remember that how bad you did the first time before you had updated all of your parameters. And then you can run that image through again and see, oh, did I do better this time? And the difference between those two is sort of what we're interested in. You can imagine if that loss decreases by a lot, then that means that I learned something from this example. My parameters were updated in such a way that I will classify this correctly with a much higher confidence next time around. So those are the kinds of examples that we're interested in. We want our network to show clear progress in terms of learning, to map from these inputs to our labels. So to put it more thoroughly in terms of, to put the automated curriculum, yeah.
So previously you said that quantification of a loss, supposing the loss is high, you say that the learning has happened, but then the loss is high in the beginning for everything, right? So basically, how can you say that something has learned is as opposed to a wrong mapping?
So you
the
can.
loss changes significantly. How do you take that into account?
Yeah, so what you would expect to see from your algorithm that's observing, how well something is doing at actually learning, you would expect to see that in the beginning it's got kind of a uniform distribution over these tasks, right? Because if you are initializing everything randomly, yeah, obviously, any step is going to probably be a step in the right direction if you assume that your training algorithm works at all. So that means that it's going to, have high success from a bunch of tasks and be able to sort of evenly split its time. As you go on, it's where you would expect to see some differences. So this is something that you can, if you read the paper that's in these slides, they actually show that the uniform policy, the policy of just training, picking a task basically at random, does about as well as these other methods in the beginning. But then as it goes on, these other methods start to have an advantage because they're picking up on patterns over time of what seems to be working well and what seems not to be working well. Yeah, so good question. In the automated curriculum learning process, you start with a set of training examples, and then we just define everything in terms of these examples. So a task is a distribution over examples. In our case, that means that we are grouping examples based off of the side information that they contain. So you would imagine one task is predicting whether or not the thing has webbed feet. Another task is predicting whether or not it has webbed feet and its feathers are oily. Those are the tasks that we're considering in this scenario. And then a curriculum is an ensemble of tasks. So that's the group of all of those groups of things that we're trying to predict. A sample is just a training batch that you draw from that task. So it would just be a collection of images mapped to those particular labels. And then the syllabus is the time-varying sequence of which tasks you're actually picking, right? So I might start off with an even distribution over all of the tasks, and then as time goes on, I settle on some that are really useful. Yeah.
Oh, so it seems like you could end up with a really large number of tasks in a single problem. Is that going to make the multi-armed very scale? Or? I
anticipated that so well. The next slide, or the slide after that, deals with that problem. So thank you for asking that. I'll get to that in just a second. So yeah, the goal is to pick a syllabus that yields the maximum payoff or the minimum regret with respect to the best strategy that you could have been playing over time. So it was 2 slides. So yeah, just to give an example of what these tasks actually are, we did this a little bit in the beginning, but task 1 we can say is the original task. Task 2 is determining that this is something, it doesn't have to be duck there, it could just be a generic like thing class. This is something that makes a quacking sound that has webbed feet, and then below you can have those tasks kind of split up. But as you say, there are potentially exponentially many combinations of that side information that you can come up with, right? So I can, if I have like 100 different nodes that are immediately connected to the class that I'm interested in, 100 different edge types, then mixing and matching all of the possible combinations is going to become computationally prohibitive, right? So how can we avoid creating exponentially many tasks? The idea that I am currently working on is to cluster these tasks into things that are semantically similar, groups that are semantically similar. So if you consider your average knowledge graph that exists somewhere out there on the web of open data, you're going to have edge types that are by nature similar to one another. So if we're considering that in the case of these ducks, I might have particular edge types that deal with what the duck's bill looks like. I might have edges that deal with what its back looks like, what color it has, what the pattern is, and also its wings. So that suggests that we ought to try to figure out a way to group these or cluster these edges together and build the tasks based off of these clusters. One way to do that is to use knowledge graph embedding. So many clustering algorithms work well on data that is embedded into some fixed dimensional space. So you have an associated real vector representation with each of these nodes and edges that appears within a graph. I'm not going to dive into all of the different methods that you can use to embed graphs. There's a lot of them. And I think that's something that a lot of people in the lab are probably at least a little familiar with. Right now, I just kind of picked the first one that had an open source implementation that I could use. It's certainly something to experiment with. But it seems, I'll show in a second, based on the tasks that it generates based on these clusters that I get, it seems like it does a reasonable job. So if we're trying to use clusters to form our tasks, we want to allow a single edge type or node to have the ability to appear within many different tasks, right? So I gave the example of the duck having webbed feet being one task, and then also identifying webbed feet and oily feathers. In that scenario, webbed feet appears in 2 different tasks there. So one way to go about allowing a particular node or edge type to appear within multiple tasks is to use a hierarchical clustering method. So in this case, we have a dendrogram, and each branch in the dendrogram indicates its own cluster. And the things on the bottom there are the original data points that you deal with. So in this case, if we're dealing with edge types, the things on the bottom here would deal with all of the different edge types that we have, whether or not it has webbed feet, whether or not it has oily feathers. And then you're sort of grouping them into bigger and bigger clusters as you go farther up into the dendrogram. So we're allowing something to belong to multiple classes and therefore multiple tasks. Yeah. I don't know that I can. It's not. Oh, no. It's not super important to see what the things at the bottom are. This is just something I grabbed to show sort of the hierarchy that you get from a hierarchical clustering. The classes on the bottom don't have anything to do with.
Well, so the reason I asked, can you go back 2 slides to your example of like one before, right? So you clustered manually, right? Based on like has bill, has wing, has black, right? Yeah. But like you'd also imagine cluster would be has bill color, has wing color, has black color.
Yeah, actually, so that's what happens in practice. So I'll show an example of some actual clusters that I've generated using this approach, and you can kind of get a feel for what the algorithm actually does. But yeah, I came up with these by hand, just for the sake of exposition, I guess. Well, tell me if you're still not satisfied in a little bit. So we have everything that we need now for an experimental setup. We collect our training data, determine the edges that we're interested in that are associated with these classes. One minor assumption, I'm assuming that these classes that were in the original task actually appear within the knowledge graph. Otherwise, I don't know, you don't have any extra information, then you can't do this approach. So then we use our knowledge graph to create an embedding for each of the nodes and each of the edges that appear in it, cluster those edges, and then we create tasks from these clusters. So sort of building up from the bottom up in that dendrogram. We start off with tasks that are composed of only one edge type, and then go all the way up to the point where everything is grouped together and you're trying to predict everything at once. And then we use our curriculum learning approach to train our model using those tasks as input. So fitting with the theme of ducks, the training data set that I'm using currently is called the Cub dataset, or Caltech UCSD birds dataset. Contains images of 200 different kinds of bird species. And the nice thing about it is it also contains side information about their appearance, so what these birds should look like. And it should serve as a good testing ground because in order to differentiate between these bird species, you would expect that this visual information is going to be very relevant in terms of telling the difference between an owl and or especially once you get down into like these there's like 30 different kinds of finch or something like that even human experts might have trouble with. The difference between one species of finch and another is going to boil down to something that's definitely captured within this extra side information. It might be something as small as the difference in beak color or something. So you can expect that side information to be helpful. So these are actual tasks that have been generated by the hierarchical clustering method paired with a holographic knowledge graph embedding. So as you can see, it kind of does group things based off of similar functionality, I guess you'd say, right? So the has throat color edge is always going to point to a color, as is the has underparts color. And in fact, the fact that they are grouped together in a cluster all by themselves means that in many cases, these two things point to exactly the same color, which kind of makes sense, right? If you're looking at the underside of a bird and also the throat of a bird, the odds that those are going to be very different is probably low. Yeah.
Unlike a RDF person, you can imagine like has throat color, under color, or whatever, all subproperties of this has color or has length.
Sure.
Or has shape.
Yeah.
So are you leveraging the property hierarchy in a sense?
No. So and that's one of the big areas of improvement that I see is that I can use the knowledge graph in potentially a more sophisticated way to get better clusters or more tasks that you can use that can be inferred from other parts of the graph, things like that.
Yeah. So just the quick suggestion, if you do go to this approach, looking at the subclass of relationships would be helpful.
Right.
And also, you might want to look at domain and range.
Sure.
Because like they'll tell you that you're talking about a bird who has a.
Yeah, exactly. Yeah, totally agree. Yes.
So it looks like the two upper left things are both like subset of the lower right one or lower left one.
Yeah. So these are all independent tasks. I did this on purpose to show that I can have tasks that only have two things, and then later on, like we saw in the dendrogram, those are going to both eventually be joined in some task that's higher up there. And the nice thing about the curriculum learning approach is that we're allowing it to focus on identifying these things in isolation initially, and then later on, if it decides that it's useful, the classifier can train on something that's more difficult, like the class like the task in the bottom left.
Is it like naturally, I guess, robust permutations of things within these clusters? Like has throat color, has underparts color the same as has underparts color, has throat color?
Yeah, that's a good question. So the way that I've structured the actual training, there's always going to be a set order in which these terms will appear within a target sequence. So the goal is to kind of hope that it learns that to predict the throat color first, followed by the underparts color.
Trying to make it permutation.
Right. Yeah. So that's just from a computational standpoint, that's a little bit different. Yeah. Yeah. But yeah, it's a good observation, and it's something that potentially needs work. Yeah.
So are you saying that like one cluster will be one task for ACL?
Correct. Yeah. So and within the hierarchical approach, you can have clusters that are as small as one single edge, building all the way up to including every edge that I'm aware of in the knowledge graph.
I don't know much about ACL, but I was just thinking, shall we make our task more like diverse, like to have more diverse edges clusters?
Yeah, so there are actually techniques, and I'll get to this in the future work. There are techniques within these multi-armed bandit problems, which is the core of what's underlying this automated curriculum learning, that can deal with an exponential increase in terms of the number of arms that you can play, so long as you have some information about how similar the arms are. And there are a number of variations that assume different kinds of similarity information. So that would be one way to sort of diversify is, okay, maybe now I can allow for all of these different combinations of edges if I know that the difference between, has throat color and has underparts color as a task is not that different from has throat color, has underparts color, and has belly color or something like that, right? The trick is in coming up with that. So this is something that I thought about for a long time and couldn't get it. In the time that I was thinking about it was how to measure the similarity between those two different groups of edges. It's not a problem that has an obvious solution, at least to me. If you have one, awesome. Let me know.
The distance between clusters.
So in that case, though, you have to have that information available for all of the. You would have to compute, like some centroid of each of these different possible combinations, and that's still an exponential time computation. So a lot of these things, some of the techniques that work on these exponentially large problems are nice because you don't have to explicitly hold all the information in memory, but those techniques don't work on the problem as I phrased it. Sorry? But you're still doing that for an exponential number of different centroids. If you're allowing these edge types to truly be mixed with any other edge type.
Basically, centroid number is a thing. So you fix it and you sort of restrict it.
Yeah. So his idea was, if you just sort of allow yourself to use any combination or introduce more diversity into these clusters by allowing more combinations of different different edge types, then if you do that, you're allowing yourself to generate an potentially exponential number of these mixtures, which is kind of what I was hoping to avoid in the first place, because it's not super trivial to deal with them. So now finally getting to what the deep model architecture looks like that we're actually training. Like I said before, I just phrase it as an image captioning problem. What this means in terms of the deep learning space is that I'm probably going to use a convolutional architecture paired with some kind of recurrent architecture. So a convolutional architecture is very good at extracting things from an image input, detecting objects, that kind of thing. And then in order to generate a caption, my recurrent component of that takes as input these features that have been extracted from the convolutional component and repeats them over multiple time steps in order to generate multiple outputs for a single image. So this is a very standard approach within deep learning. And as was touched on before, it's a common architecture that's used to attack all of these tasks, right? So the idea is that I want this same architecture to have information from all of these tasks embedded within its parameters. So I have some real early results. This is the entire slide, so don't get your hopes up. So I haven't done any testing in terms of like accuracy on a test set, but observing the behavior of this thing as it trains. So this is again a deep architecture that's wrapped within this automated curriculum learning framework with the tasks being generated from the knowledge base. So tasks with lower edge counts are preferred early on in training. It's to be expected, right? It's easier to predict a sequence that's only 3 things long as opposed to 30 things long. So it focuses on things that you would expect to be very visually obvious, like color, and then kind of progresses onto patterns, and then others. I wish that I had time to throw a graph together, but I couldn't. And I'm tracking the validation accuracy as I go along, and it seems to be doing pretty well so far. 85% classification on this data set is no joke. Yeah.
So is there like a baseline for validation accuracy?
Yeah, there's a number of methods. I think state-of-the-art gets close to 90.
On this particular data.
On this particular data set. Yep. And I think the best that you can do on this data set is actually 96 because of like some noise that's been introduced. So 85 is not bad. and it's a fairly simple architecture, and it's not done training yet. So who knows? I might get better.
So how do you measure the accuracy?
So this is on the original task. So just mapping an image to a single class output, and then was it right or not?
So you are treating your task as image captioning task. So like for image captioning, I think so. One image is associated with for example, a sentence. And in your task, for one image, you might have a set of labels, and each label is like short text, and so you will concatenate them together.
So it's just like a one-word sentence. So the original task, I'm predicting just a single class for the image, right? So I take the architecture that I've trained, and I just have it output a single token, and limit it to being within the original vocabulary. So it's predicting a single word that exists within those 200 original bird species, rather than forcing it to generate a longer sentence by continually feeding inputs to the recurring architecture.
So is your output a sequence of words or?
During training, it's a sequence of tokens. During validation testing, it's just a single token, because I'm just evaluating its performance on the original task.
Okay, I see.
Yeah.
Are you so with the objects of you're just treating them as plain text literals, and you're basically training it to identify that one literal. Are you doing it? Is there any cleanup needed of that? Or is that?
If you have like multiple literals per.
Yeah, so like either like spellings or.
Oh yeah, I do like. Yeah, I do some basic preprocessing, looking for like typos and that kind of thing. I did a little manual cleaning on this input, and but because this was developed specifically for this domain, I have a knowledge graph that's fairly clean. There's not other people contributing to it. It's not changing as it goes along, so I don't have to worry about that as much as if I were to let this kind of approach loose on something like DBpedia.
So in your training time, so the output is a sequence of words. So does that mean you have a decoder at in your network? In the inference time, the output is a label.
Yeah.
Right. So then
so
you have
outputting a sequence of words is the same thing as outputting one word just at multiple time steps. So when you're doing it like an image captioning task with a recurrent architecture, you're just feeding in the image inputs over and over again until it's generated as many words as you want it to.
In the inference time, you make your network to just output one.
Yeah, so that's just a result of me only giving the image features to it once and then saying, no, you're done. And I also restrict the output vocabulary to the highest that appears within the 200 original classes, so that it has to pick a class, essentially.
In the inference time, the output vocabulary should be the set of original labels.
Right, so rather than doing all of the vocabulary words that I have for generating these sequences, what I'm saying is I ignore all the other ones, and I just take the maximum of the ones that appear within the original task.
I see.
Yes.
So regarding validation accuracy, I was wondering about, I guess, lower bounds as well as upper bounds. So like, how well does like pure random or like the vanilla neural net do?
Pure random would be 1 out of 200, and
Like
a vanilla like 3-layer CNN or something. I'm actually not sure. I know there was a paper that used a neural net that had been trained on object detection using ImageNet as a training source, and then just fine-tuned it a little bit and got really good results. So meaning that some of those features were useful for predicting birds. I don't remember exactly how many. You'd have to look up the papers that cite this data set for an accurate range of values.
Maybe I missed this, but in your hierarchical cluster, how did you choose the final number of tasks? Because you have to do like some threshold to on the.
Anywhere there's a branch forms a task.
Oh, so you're using every possible?
Yes.
Okay.
Yeah, I'm not picking a level to set the cluster. So yeah, does fairly well. But let's say, I want to do, so one of the things that I was interested in the beginning was whether or not this kind of approach, giving this extra information to a classifier, can help the classifier beyond that original task that it was given. So if I have these, a data set of classes and a knowledge base, what can I do from the output of this network besides just classifying better? So one way to look at the approach as I've described it, I think I'm over time.
It's okay.
Apologize. So one way to look at this is as a means of letting a perceptual model, something that only has access to the information within the image as input, determine which things it can identify well, and then leaving the things that it can identify well for some process that happens after the training. So for example, inferencing over an input and some knowledge graph that I have. So this is the view of things that kind of ties it into my thesis, I hope. So along those lines, what I'm forcing the model to do is to produce different representations than what was initially given for that classification task. And I can help guide which representations I want it to do well on by essentially varying the loss signal that I'm using within the bandits algorithm. So what I mean by that is, if I know that I want my algorithm to perform well on predicting only these initial classes, then I have a means of heavily weighting those initial the tasks that contain those initial classes, so that I'm sort of forcing my architecture to care very much about doing well on those tasks. So that kind of gives you a mechanism. If I can do that weighting for that original task, let's say I change my mind later on and I want to use the same training data set to now train a model that's good at doing something different, then I can, if I have an intuition as to what tasks will be useful for that different thing that I'm interested in, I give those things a higher weighting. So it kind of gives you a flexible means of generating different representations that you might be interested in. And we'll take an example of that. And this is just about the end. I promised there would be pasta, and there is pasta. So let's say you're given a data set that has images paired with a pasta label, specific label that's saying what kind of pasta this is. But you decide that your task, I don't really need something that tells me the difference between linguine and ziti or something like that. What I would really like is something that can tell me whether or not it's healthy. But I still only have, as my original training data set, images paired with these associated labels. In the original formulation, or in the classification formulation that most people use, what you're going to end up with at the end of training is something that can tell you, hey, this looks like ziti, or hey, this looks like linguine, and might not even do that great of a job, because it might be a very hard problem. Telling pastas apart from one another is difficult. I'm not an expert. But rather, if I have these different formulations of these images that I'm originally given, I might be able to do better at telling the difference between a pasta that's made from a vegetable and a pasta that's made from something starchy. So maybe I can't tell perfectly the difference between egg noodles and spaghetti, but I can tell you that both of those are not as good for you as like a zucchini noodle. Yeah.
So, looking at this data, the question is, why are you so? Images plus text can be a good combination to train a network, right? Because text is also going to be rich, and then description of pasta can basically help classify better as opposed to just the image alone. So doesn't we like just thinking of exploding like the combination of image plus text?
So this would be so what I'm hoping to do is use the approach that I described before, where I have multiple labels that might be associated with a single input, and train the model so that it can produce these different outputs besides just a single label associated with the class, right? So if I can say this pasta is a vegetable based as opposed to something else, then that might help me in a task of identifying things that are healthy versus not healthy. So it's basically the same scenario as before. It's just showing that, rather than just doing well on the original classification, rather than using the side information as a means to get to the original classification, I might be able to take this approach and repurpose things a little bit better than if I had just trained on the original classes. Yeah.
So like from this table,
so this isn't an actual data set. This is just an image of pasta that I found. I just want to. I'm not training on like I wouldn't create a task that says like predict the amount of carbs that appears within this pasta.
right, but if you had annotations like zoodles has calcium this much or has calories this much, wouldn't that help you with the deciding which one's healthier?
Yeah, you have that information in the knowledge graph, but this is sort of the point of using the curriculum learning, is that you're probably not going to be able to train a classifier super well to tell you how many calories are in an image just by looking at the image, right? So sort of when I was saying taking an alternate view of things, splitting apart the perceptual information from the information that I can use to inference later on, the curriculum learning should give me the things that I can pick up on that exist within an image, like, oh, zoodles are green, that's probably vegetable-based. And then later on, I can use that to infer, okay, vegetable-based pastas tend to have this much calcium or this much vitamin A or vitamin B. And I get that later on information I can get from the knowledge graph. So it's just kind of giving me a hook into the knowledge graph, if you will, from the information that I can get visually.
This could be super useful in classifying medical images.
Yeah, maybe.
Micrographs and things like that, where you're trying to pull out quite a bit of information.
Right. Yeah. So I agree. Yeah, leaving things for. So this is kind of the crux of my thesis, is that if I can separate these two processes and let CNNs do what they do, and inferencing do what it does well, then I can use them together in a way that enables better performance on tasks. And so that's kind of the point, is I try to leave the visual stuff to the CNN, and then if I can get good things out of that, then I can combine it with something that exists in the knowledge graph that might help me later on. Sure.
Have you thought about the explanation side of it too, since you're training on specific features, you then use it to say, well, I noticed that, I noticed this, and I noticed that, and because these two come together, it does.
Yeah. So that's something that the other Jim suggested, was that this could be very useful, or he didn't say that, but he said that it might be helpful for sort of an explainability side of things. If I'm producing a sequence of features that I think I see within an image, it could give credence to a final prediction, or it could make you doubt the final prediction. Right.
This is the first time I've seen it.
Yeah. So you kind of get some implicit explanations potentially if we're talking about sort of like symbolic explanation, so something that's phrased in terms that a human can easily interpret. So for example, if you see a caption that says the man is wearing a shirt and shoes and pants and has 2 ears or something like that, then that's probably pretty good indication that it did correctly identify that it was a man, assuming that you're not just getting some
Looks like
linguistic.
A duck and quacks like a duck.
Right. Yeah, duck typing. Exactly. I'm glad somebody got the duck typing reference hidden in there. Yeah.
I like this work, but it seems to me that you are not actually doing image classification, but you are doing image captioning instead.
So they're the same task fundamentally. It's just that image captioning is image classification at multiple time steps.
Yeah, but I don't know. But for me, it's a little bit different, and also I think that it's not consistent between what you are doing in the training time and the inference time.
It's not.
Yeah, and I don't think that's a good strategy. So my suggestion would be that maybe you can change your loss function to make it a real classification task. Like you can use some.
Yeah. So one thing that you could do if you wanted it to truly be a single output of a class at a single time step and ignore any
not
recurrent.
really that, but like you can use some merging-based loss functions, like so you can pick up some true labels and randomly pick up some negative labels. Then to just, I mean, you can use the merging-based loss function, like to make the positive labels have higher score than negative labels.
Sure.
Then in that case, you can have arbitrary number of labels in your training time.
I don't know that that's true.
Yeah. Why don't you finish up?
Yeah.
And then
We'll take that
can-
offline. Yeah. So potential improvements, more sophisticated task generation rather than just using the information that's immediately available around surrounding a class in a knowledge graph. You can do more interesting things like, analyze the domain and range of various properties and use properties like transitivity to get extra tasks out of things. And that involves also handling less clean data sets well. So if you have stuff that's mixing classes and literals and whatever else. And then there are potential bandit algorithm choice improvements. So the one I'm using now is just for simple adversarial bandits, but there are more complicated tasks. And there's actually a good amount of research that's been put into bandits with exponentially many arms. One of the big applications of bandits is in advertisement placing. So there's a lot of money in that and therefore a lot of research.
How appropriate.
Yeah. And then, like I talked about it towards the end there, weighting different tasks differently based off of, during the training process, based off of what my end goal is, rather than just predicting a single bird from an image. Maybe I'm just trying to tell whether or not something is healthy. So yeah, we already kind of had the discussion time. I'll take any more questions if.
Well, why don't
we can take it offline.
Why don't we thank Matt and then
Obligatory image sources.